So Sebastian, thank you so much, and the stage is yours.
Thank you very much for having me. Also on behalf of Professor Aßmann, who's sitting with me. He's just not in the camera focus, but he's over there. So let's start it. Right, so I'm talking about distributed patterns for robotics today and how we can aid the programming of robotic applications with it. And I want to start my presentation with one word, which is trustworthiness here, and which itself is the degree of confidence that exists in software requirements. And that's a definition which is long around there. Everyone somehow heard of it in different ways. And today we are asking ourselves here, okay, how can we actually create trustworthiness for robotic applications? And to do this, to solve these problems, to gain the trustworthiness, especially in cobotics, we are required to solve basically 3 different problems, which is firstly, we need to answer the question, always to the user, why a robot is doing something. The second thing is he actually doing the correct thing? And the third thing is, what will the robot do next? So the past, the present time, and the future. These are the things a user of a cobotic applications or collaborator needs to know. But these things are actually not that quite easy to achieve, because we have many dangers firstly around there, in especially cobotic applications, because we don't want to harm humans or the environment, or the most expensive thing, probably the robot itself. Many things are really complex around there. We have distributions, so multiple robots, maybe sensors around there. We have heterogeneous hardware, especially in research. We are tackling these because we're mostly trying to buy, of course, like not the most expensive robots all the time. And the third thing is we have to bring many guarantees with us. We are required, for example, to have timing guarantees, for example, real time. We need to handle behaviors and faults based on requirements of the application itself. And context adaptations are really important, especially to react to the world surrounding our robots in the end. In our work here at the chair, we are basically looking at 4 different aspects to provide trust. And the first one is correctness by construction, where we mostly work with model-driven development and model checking, which is second, the debugging of robotic applications, where we use tracing and model checking to gain more insights on what an application is actually currently doing around there in the world and at the development time. The second thing is the forecasting, so we can look in the future of the robotic behavior, which is, for example, possible with runtime modeling, because we can see what are possible next steps. And finally, safe, underline safe, context adaptation. So if we change something at the system, we of course want to make sure that it stays safe. And there we work with formalized interfacing, basically. And if we want to model such a system, we have different modeling requirements around them. So we need some kind of formalism there, which provides everything which has a robotic word, which is non-determinism, which is basically the case because the universe is non-determinism, so everything around the robot also, so everything can happen at all time. And we have asynchronicity, especially in connection to concurrency, because we have distributed applications which interact with each other. But on the other hand, we have timing constraints, because we may need to sense data in a certain timing interval or have real-time constraints. And everything needs to be extensible and modular, because these robotics and also physical applications, they're usually getting extended at runtime. So at runtime, development time, sorry. So we need to somehow tackle this problem. There is one formalism around there, and I think I spoiled it a bit with the title of that presentations. So it's surprisingly, and not surprisingly, Petrinates here. They are by nature already non-deterministic and asynchronous, and also provide concurrency based on the structure. We will have a look soon on that. there are many extensions around them in the world, especially because people are researching on that thing longer than I live, maybe also longer than my professor is living on. But based on this extensibility, we can like grab out what we need, build our own formalism which suits our needs that we have. And based on these extensions, when I look on it, they are also modular. Okay, so now we have formalism, and we want to apply that to some robotic applications. And within this presentation, we will have a look at two of them. The first one is a really simple one where we have just two robots which are sorting colored objects in the center. So on the left side, they can't reach both sides of the system, but they want to sort depending on the color in their boxes. So what we want to achieve in that application is a safe collaboration. So when a robot is entering like the center zone with objects, it's not allowed to crash into the other robot and vice versa. That's the story of that. And the focus of our example there is mostly on verification of communication between the robots and the verification of disability workflows. Literally on the other side, we have the mobile cleaning, which we did in just a small simulation as part of my thesis currently, which is a mobile robot with a really weak battery. So that's the story. It's weak battery, always dying, which basically drives between three locations: a charging station, a pickup location where it picks up objects from the desk, and a drop-off location where it puts picked objects. And the task is like to clean one desk and put it in the box, basically. But it has to charge in between always. So we need to make sure that we don't die somewhere on the way in between. Okay, so that's the story. That's what we are following today. But before we dig into it, we of course need to like, get a glance of what fundamentals we are using. The first one, as promised, are Petri nets. In a nutshell, a Petri net is basically a triple or orbited graph consisting of places marked by circles. They are basically distributed states, which may contain tokens, number of tokens. And the second thing we have are transitions. And these transitions are marked by bars and consume basically tokens from their input places and produce new tokens in their output places. Transition can just fire if every input place is marked. So that's the story. It's a quite simple formalism, and it's quite easy to understand, but of course for more complex systems hard to master. One of the big extensions around there in the world were introduced by an ISO standard, the pattern markup language. And what we're using here in our presentation today are pages and references. You see one here as the example. They allow us basically to modularize Petri nets within these square shapes that we see here and connect them by references. So for example, on the left side, the place pget is referenced basically from another page. And of course, this can be also done with transitions with the same schematic. So then we have like a dashed transition referencing a solid shaped transition. The second and also last extension that we'll have a look in the foundation are time Petri nets. There's many extensions around them in the world. I think they started somewhere in the end of the 80s with some kind of bunch of extensions there, but there are basically three schools. The delay-based Petri nets, where we specify a firing interval where the first number here, in case it's 2, defines a minimum delay, and the transition cannot fire before that time. So if it's enabled, it can just fire 2 time units after it's enabled. And 5 in that case is the latest firing delay. So after 5, it can't fire even if it's enabled. Duration-based Petri nets, they consume a token always and keep it like inside of them. In that case, for 5 time units, and then produce a new output token in each output place. And the third and last school are interrupt-based Petri nets. The idea of them is that we now save the timing information within the tokens, so tokens are not equal anymore. They are identified, they have timing information. which also means that it finds that some kind of autonomy. So the question is now obvious: what are actually the benefits here? Why do we want to use such an old, dusty formalism around there in our brand new cobotic world? And there are many benefits around there. If we have a look at the modeling part, they basically give us the ability to reason about reachability of states, liveness, boundedness of our system, especially, for example, communication channels, but also on invariance and execution paths. And we can do that on the modeling level, which is way more practical solvable than when we start from the bottom up by coding, because we have to analyze a less big state space than a pure code analysis. If we have a look on examples, what we can do here with robotic analysis here, reachability can be, for example, used to check if the robot can reach a faulty state. So is it possible, for example, to have the engine of the mobile robot running at full power and the brake activated at the same time? Then we have liveness constraints where you can check, for example, deadlocks. So we are blocking each other maybe in the access to the shared space or whatever, and also liveness. So is some action maybe always possible if you want to have maybe like a fail-safe action, which always stops the robot. Boundedness, I think it's a classic example, and that's why I'm also using it here in the presentation to use it for communication, because communication usually bounded to some kind of capacity which cannot be exceeded, and we want to guarantee that. Invariants, they basically take a similar problem. So, for example, you often want to make sure the robot can be stopped. And paths, they are like a good thing for debugging, as earlier mentioned, because we can check how we reach some certain states. Based on that, gain information about what our application was actually doing or will maybe do in the future. Okay, so far the patterns, why we can use them, what's good on them, even though they are old. So let's get a bit more into the present and the close by past. The robot operating system is the framework we're using at our chair for developing robotic applications, and it's also de facto standard robotic middleware. Many of you will probably know it already. So just to keep it on the meta level short, it's a middleware providing hardware abstraction, communication, and also based on like bundled libraries for planning of robotic motions and much more functionality. It's multilingual, so you can use it in many languages. The most used ones are C++ and Python, but there also exists bindings like in Java, for example. Around there are two major versions, where in between the communication design was redesigned, and also some certain things were much more standardized, even though the base structure remained the same. But that was in our research actually a challenge to overcome, because we started everything was one back then, because all of our robots were like running this system, and it was also like the major version used back then by many other people. So not many libraries were already shipped. So we used it basically for the to check about communication and context adaptation back then. And when we transitioned to ROS 2, we had a look on, okay, what can we check there? What is new? What is different? And what they changed and a big block was like scheduling. So an entire new mechanism was introduced there. And that's why we focused there in our ROS 2 works on scheduling and time guarantees, even though we integrated our past work in that too. And to achieve that, initially we started with the normal patterns we just saw for the communication context adaptation, because we mostly were using boundedness analysis there. Look on that. And in the second part, we went for time patterns, especially because of the timing guarantees. So how's ROS structured? Again, in a short nutshell. Basically, that's how a ROS package looks like, right? You have some nodes, so they are connected by topics, which are a unidirectional communication mechanism for services, which are basically a request-response-based pattern. And such a node is basically a single process that performs computation and exchanges messages, as already said. And in terms of topics, we have in ROS1 configure capacities, and in ROS2 we have quality of services, even though that ROS2 is basically a superset of ROS1. Right? Packages around there are just the basic unit of organization and structuring that we have there. So that's basically how such an application looks in the wild. So let's get a bit more into what's new in ROS2 and what we researched on, which is how ROS2 handles scheduling and callbacks, how it's doing that. And the single source of a trust that you have in scheduling and ROS2 is basically our weight set, the weight set of ROS2, which manages newly incoming messages. So we have basically our flow-based types in there that we know, like subscriptions, services, replies of them, and timers, and potentially also guards, which can be extended by the user and provide a certain mechanism. But we focus here on the first four ones, which are the basic patterns which every application has in common. The scheduling in ROS itself is like a pyramid scheme organized. So on the lowest level, we have the callbacks, which are user-defined function. So most of the systems, they handle messages, process data. So for example, a subscriber could that be, which receives a message and processes it, does something. And these callbacks can be grouped into callback groups. They are containers, and they also define the execution order on the second level by the adding order to the node. They can be of two different types, so either mutually exclusive, or they can be accessed in parallel when we enter groups. These callbacks and callbacks groups, they are organized then, scheduled by executors, which are either single or multi-threaded, depending on what you want to do in your application. And below that, we have basically our middleware, which is, in most of the cases, but also exchangeable now with the latest versions, is DDS, which is like the low-level middleware, which handles communication between the nodes and is fully decentralized, but still real-time capable. So how does such a scheduler actually look like? How does it bring our messages that we may receive from outside the world into our callbacks? In the case of a multi-threaded scheduler, here shown in a simplified way, basically it's like an infinite running loop, parallel, of course, depending on how many threads you have. So basically you start by obtaining a log to the weight set, and then you check if you have something. If you have something, you basically walk through the weight set, grab a callback that you can execute, that you're able to execute, that you can execute it, sorry, means that the group is accessible, so no one else is using it in case of a mutually exclusive group, and that there's a message available. If so, we are clearing it from the weight set, we are accessing it, we are releasing the log and loop around. If we have nothing, then of course we need to like refill the weight set in our left loop here with the purple box. So that's in a simple way how multi-threaded scheduling works. There's also a single-threaded version, which just does not have these logs because we don't need it. So, like destroying applications in ROS, which are using these schedulers, is quite easy. I think you can do it in 3 lines of code. Let's have a look. That's how you can do that. So now we are coming basically back to our mobile robot driving there. So let's imagine we have a single thread executor here. I'm sorry, a multi-threaded executor with one single thread, most precisely. So let's think we have like a drive callback on the left side. So that's what the robot is controlling, driving around between the objects. And now this callback calls a service which has to check the battery. So we want to know, okay, do we need to charge soon? The problem now is we are running actually here in a deadlock. And that's because we don't have a second thread to run the system. Our only thread is basically occupied by the driving callback here. So we send the message out, but nothing comes ever. So destroying the ROS system in 5 seconds, basically. right? If we want to model such an application, or a ROS system in general, we have to think about multiple aspects. And especially we have 4 aspects here, which are communication, execution, structure, and interfacing, while communication execution are timing sensitive. Communication, in our case, is about topics and the services that you just saw, and maybe also about quality of service constraints, especially in those 2. The structure is about our nodes and packages that we just saw. The execution is our intra and internode control flow here. The scheduling, especially that we just had looks or the single and multi-thread versions of that. And we have to care about interfacing because of our applications communicating with the outside world. So we need some kind of formal interfaces there to safely adapt our application. And as already shined through, communication and execution, they are timing sensitive because our workflows are maybe time dependent. We have the scheduling and we have also adaptations in them. So what are the benefits here to for Cobotics and ROS applications to model this? In terms of communication, we can do 2 things basically. We can detect message loss, for example, topics, and we can detect disruptions, even before system runtime. And we can construct correct communication patterns by default, right? We can specify them, we can check them, and if they are correct, we can generate a system based on. For the structure, we can detect, for example, unused nodes. We can reuse models for different nodes more easily, and we can generate whole packages. On the level of execution, we can debug specification derivations before we run the application. And we can also debug concurrency issues, as we just saw in the example, for runtime and at runtime, which you can also use for forecasting, because we have a runtime model maybe of a Petri to look in the future, what are possible maybe next transitions, which may fire. And in terms of interfacing, we can create verified and trustworthy context adaptations because we can describe them formally with the Petri nets and interface them based on. And that again enables us correctness by construction because we start with a model and end in the code. So how do we do that? And the answer is probably my PhD thesis. Maybe someone in my defense later on will say that's not the case, but I hope that won't happen. So how does my work function? It's co-distributed patterns to ROS, and if we start having a look at how such a system would look like at the runtime, before we dig into the development process, what we would have is we have some ROS nodes controlled by patterns on the left top side. They are safe. They are trusted because we check them. On the right side, we have a coordinator, which is able to change the nodes based on context adaptations, and context changes and timing informations. And of course, somehow we need also external interfaces to the new robotic components, again, based on message interchange, possibly by topics and by services. So that's the classic ROS part. That's basically how you access move it in the end from these ROS nodes. So what is a suiting pattern formalism for that to solve these problems? As I already said, there are many around that, especially in the timing world. And the most suiting pattern formalism for that was invented in 1996. So in this year, it's 30 years ago. And the idea of this is basically that we require robotic actions to work in a timing interval because we don't know how much something takes. So maybe like the driving of a path takes half a minute. Maybe it takes 10 seconds. We don't know. So they may take longer as expected. And the second thing is actions need to consume resources immediately. For example, access control to the engine or the joints of a robot or to some shared source. So this needs to be also exclusive. And the type of patterns introduced by Heiner in 1996, they do this. Here we have an interval again, but it works differently. So if we have a look at T3, for example, 2 and 4 do not specify like a wait interval. they specify a duration. So the firing of a transition takes 2 to 4 time units. So that's the possibilities in between. And that's also what it's, what is different to the other modeling techniques that we just saw. The time itself here is not like a real clock, how I imagine, but it's more like a logical procedural clock, which helps us to keep the state space small, which is a common problem. In the narrows itself, we use this formalism multiple levels. The top level, this is the model that we see here. The user basically specifies the system. We have later look on an example. It contains our communication channels. It contains the scheduling definitions, so what type of scheduler we use, etc. And also pages representing our packages, nodes, and much more. The runtime model is basically like the cutted version of it. So one node for one ROS node in the end, basically. So we cut out the channels and just keep the interfaces to them, because we use the read channels, of course, then in the implementation. And the patronage model is then like a transformed version down to a normal patronet, which does not contain any of our customized introduced modeling elements from the system. So that's a model checkable model at the first way. And finally, we have the automata model, which is just the automata representation of our patronage model. That was needed in our work because there was no model checker existing for the patronage formalism that we just had a look on. So we had to extend it. In our work for the patronage model, we use TINA, which is the state-of-the-art model checker there. For the automata, we use UPAL, which many of you know, and which is also the state-of-the-art model checker in that field. If we have a look on how these models change and their properties from top to the bottom, we can see we basically refine from top to bottom. So we add more details, we add more information in it explicitly. And if we go upwards, the abstraction always increases because we're introducing modeling elements, but we also increase the modularity and understandability because we don't need to model automatas and basically the channels by hand all the time. So let's have a look at the bottom transformation. How do we do it? Transforming patronets to communicating automata can be done basically by introducing one single automata for each transition, which communicates based on signals to the other transitions which are connected to it. So for example, if T1 fires here on the left side, we can see in the top automata on the right side that we fire, which is marked in blue, channel T2, which means we notify every other automata listening on it. And the bottom automata is listening to it, which is a T-end transition. So on the left side of this automata, it takes it and then increases in the running state its marking. So that's how you do it basically, and how you break down the nodes. The system model, to go back to the top of our modeling phase here, contains much more abstract descriptions. And the first ones of them are basically our channels, which are the first manner service channels. We see it here as an example on the bottom side, which is connected to our sorting example, where we have a peak service with server on the right side, so the channel is in the center, and the server is marked in green. What does that mean? It's a prototype page, which means at runtime it represents multiple pages, one for each potential server instance in the end. Because in ROS you can have multiple server instances for the same service in the end. And on the left side we have client pages, which represent, as said, basically the clients. It's a bit more simple in the world of topics, because then we don't have instances. So there we basically have our topic in the center, which has in its ports, which are on the left and the right side for inputs and outputs, channel capacities. And these capacities, they represent the capacities that you also have in the ROS application. And they are then connected by references to our subscribing and publishing nodes. So far to the communication. The second thing you want to model on that level are basically context adaptations. So how are contextual interfaces handled? And for this, we take a look back to our mobile robot example. On the first side, we have input signals, which are binary, which are attached to transitions and which are combined in clauses formed as conjunctive normal forms, which is essentially important because we can transform them based on their similar structure always down to a patchnet. So they can be replaced so they don't change the patchnet semantics in the end. The example is shown here. So the IC check signal enables our T0 transitions if we don't have a battery fault and if we are either in the battery mode 1 or battery mode 2. Vice versa, we have output signal clauses which are attached to pages representing our nodes in the net, and they are much more free in their structure because we can just omit them in the action model checking because they don't add some semantics actually to the execution of the net. They just produce output. So we choose to allow their comparison of markings of places there and also the usage of arithmetic and logical operators. Example is shown at the bottom side. So the OC check clause produces the output true to the outside of the world if the marking in the place battery stages is greater than 1 or the marking in the place P2 is smaller than the marking in the place P8. So that's our small and smooth context adaptation mechanism there. So now we talked about like everything around the node and how we adapt these nodes. So how do these nodes actually look then when we model them as a developer? And for this, we stay in the same example and have a look at a cutout of it. So what we see here is a mobile robot node out the top, for example. And this mobile robot node contains some orange callback groups. These groups have properties shown in red, which are the type of the group, so maybe exclusive, maybe re-entrant, and the priority. The priority basically, which is also attached to the callbacks, is representing the adding order of callbacks to groups and groups to pages. And this is necessary because we don't have like in this flat modeling style on the paper, like a timing or adding order paradigm. And these groups, as said, they contain our callbacks, which are maybe purple marked timers, blue marked subscribers, or as we already saw, green marked services. They share a common structure, essentially timers and subscribers. They have always a starting place and any transition, and all servers have a starting place and the ending place. So that's basically the constraints that we have on modeling there to keep it in the format of a ROS application. So that's basically how we model such a system. That's how we model nodes, how we connect them, how we adapt. So how do we integrate it in a model-driven chain in the end? And to do that, we defined here 3 roles, which is the modeler, the system engineer, and the developer. The modeler does what we just saw. He creates such a model. The system engineer, he's responsible for model checking such a model. So basically using model checking tool to see if the quality of the model is sufficient, does it meet its requirements. And on the lowest link, we have our developer, which creates based on our runtime models that we can generate out of the system model. Actually, extended package with actual code, which then controls the robot, and which may also produce runtime traces, which are again analyzed by the system engineer. So that's the story of our model-driven chain. And there are many tools behind there. So I always foreshadow before the next slide that I'm always scared of showing the complete tool chain because there are many models and tools in there. So we keep it slowly here. And that's why I also grayed out some parts. So what we see for now here are 4 lanes for modeling, model checking, implementation, adaptation, as we just saw it. And on the left part, we see our 4 models: the system model, the runtime model, the patchnet model, and the automata model. So far, we know everything. The tools which are in the chain then are the flattener, transforming our system model to a patchnet model, automata builder, which does the transformation from our patchnet to the automata. And third, the splitter, which does the transformation of the system model to the runtime models, which are later integrated into our nodes. So these are the basic tools running model transformations. Next, we have then the package generator, which picks up our runtime models, generates a package, which are later extended by the user, and which contains a patchnet engine actually running the system. So the system is run by the patchnet, not the developer controls the model by himself. Then we have on the model checking lane, trace visualizer, got a trace visualization, which takes out the traces which generated by our runtime application and by model checking, and interprets them, visualizes them. And they look different. Basically, there are two types of them, depending on what we want to have a look on. If we want to have a look on the communication, so we want to debug it, we want to check are there maybe communication flaws, it looks that way. It's a big diagram with many lines, and if you have a long-running application, one of the diagrams which never fit in any PDF page in any pieces. But what we do here is, what we see here is linked-based pairs, left on the left side, basically a pick and a place operation, right? So we have a sensor running all the time, a regular task, and we have some pick and some service called. On the bottom, what we see there is basically the number of transitions fired. A bit higher, we see the fired handler attached to transitions. So maybe we have a transition pick or pick success, which does something, doing the actual picking, for example, accessing the robots. Above that, we have topic usages, the signaling behavior, so our input signal, how they behave, how they change the value. Service executions, basically these big brackets. So we have, for example, right on top a grid control service, which is called. And this especially also contains information about the client and server instances used. So this is how we debug communication at modeling time based on these traces. But this does not actually help us to have a look on how the timing semantics behave. And there we choose a different way on how to analyze that. And that is shown here at the example of our mobile cleaning application. For example, we have a look on the right side, we analyze the timing of transitions. So we can check, does the transition fire in a certain time after another transition, which can, of course, generalize also for callbacks. That's what we did here, for example, on the right side. On the other hand, we can also go for the ordering of callbacks. This is done by attaching an additional automaton, which is on the top lane here, which is orange marked, and changes its value based on the transition fired. So that helps us to detect scaling and timing defects, and also the influence in the end of groups, which extends then to node local and cross nodes, because we can generate these traces also for multiple nodes at the same time. This was now at modeling time. We will look later on at the runtime. The last part of the Dineros toolchain is the adaptation line on bottom. Basically, we have there a coordinator. We saw that initially. He receives the signals we just saw. He also receives the traces we had a look on, but he also receives forecasts. So basically, the engine communicates with the outside, hey, these transitions will fire next. And based on that, developers can extend the coordinator to implement policies, deciding what to do. So how to change input signals, for example. The last part of Dineros, which is not part of that toolchain, but used basically for application, is the engine. The engine basically works by attaching first the handlers to transitions. So they are basically taking over the tokens, doing things with that, and processing output tokens. But these tokens, they are not normal tokens. They are balloon tokens, which means they contain data, which is not an entirely new concept. There are colored patchnets and many of these around the world. But balloon tokens, they basically say that you have a common format across all the tokens, which means you can make them opaque for the actually execution semantics and do not have to integrate into the model checking, reducing state space growth in the end. Right, so that's how the transitions work, how they receive tokens and send tokens. The second level where the user can interfere is on deciding which transition may fire. And this is done by execution threads. So there is a number of threads. The number is defined by user. And he can, in the end, say, okay, I got these number of transitions from the engine. Which do you want to fire? And then the user can decide. So, and by using this mechanic, we basically preserve three properties, which is non-determinism, because handlers and these threads, they do not change the eager firing logic. We have a data flow based on the balloon tokens, and everything is distributed because we can run across the engine on multiple nodes and they can communicate based on tokens. Summarized on the transformations that we just saw, we have basically 5 transformations here. The flattener, which is like an additive transformation, basically a refinement because we replace channels and signals by pattern elements. The splitter, which is again a refinement, and the additive transformation actually creates multiple models out of one model. We have the generator, which is model to code basically. In our case, it generates for there was 2 applications Python code, and for our initial ROS works, we generated Java, ROS Java code. Then we have the tracing, which is also some kind of model generation because we generate a trace model. And finally, the automaton builder, which is again model transformation, one-to-one. Finally, I want to have a look on the case study on our case studies that we just had. And this is the part where we have looked at some big fucking Petri nets. If we keep the safe palletizing in our mind from a really abstract view before we go into the Petri net, we use basically 5 components. So we have a selector, which is basically the user telling the robot, okay, sort this object. We have a controller, which is our central workflow, a synchronizer, which makes sure that we don't, that both robots pick at the same time in the same space. An executor representing the low-level picking and placing API. Sensorics, which check if a user is interfering so we can stop at any time. And also on the left top side, a feedback component, which is essentially a screen printing I finished the sorting operation. If we glue everything together in a Petri net, we end with that. And that's already the reduced model. But we see here in the end are basically the same components. So on the left top bottom side, the executor with our low level picking and placing, a safety model on the right side, on top a synchronizing component, on the left top side a selecting component, and a central workflow on the top center part. So how does a trace look like if we want to debug such a model when we use it as a runtime model? That's how it looks. And it looks quite similar, but there's one essential difference, which is the bottom line. The bottom line is not now not the number of transition file, it's the real time there. So it's time in seconds actually. So we have a 10-second runtime there to pick and place. So initially the robot gets the control on the left side there, picks, places, and while he places, another robot tries to acquire the control. He can't do it, so the other robot continues his task and ends the control. Right. And however, I edited the second time. Sorry for that. For the mobile clinic example, we are currently in the works on implementing the runtime debugging, but the application essentially looks like this on the top level. So we have a controller node running our workflows for picking, placing again, charging, and reading reports. Reading reports means you can look on the right side, getting reports from the robot about the battery stages, the sensor stages, and anything else. And this robot also basically provides services for driving, picking, and drop. So it's a low-level API. So that's the essential idea. And for charging and selecting, we have our own nodes again. If we model that with a Petri net, this even grows more. But now we have it much more compressed into basically Cobotics. So basically, that's the same. And now I'm happy that I gave to Wolfgang the slides, so you can have a look later on in detail on the Petri net here. But what we see on the left side here is our robot node, which has some really similar looking callbacks for checking the battery, sending a report, and also services for picking and placing and driving again, which are accessed by our controller node on the right side. I omitted here pages with the same structure. So if you don't see Petri net, it's essentially the same structure as the one above. Okay, so summarized, how do we provide trust in our work here? The first question was, how do we provide correctness by construction? So we have the immerse NDA, which produces our code in the end, and which uses the model checkers Tina and Upan, depending on the model that we in the end use for model checking. We have debugging of robotic behavior based on static and runtime tracing, especially for communication and for concurrency issues. We have forecasting of robotic behavior by using our time Petri net contained in the immerse engine, because we can see what happens next, what is maybe executed next. And finally, the safe context adaptation is provided by our input and output signals, which can be changed by our coding later in the end. Well, thank you very much. I'm bad at ending presentations, and I hope at least 10% of you are still awake. So thank you very much for having me.
All right, we have some time for questions. Maybe we start in the lecture halls again. KIT, do you have any questions?
Yeah, we don't have any questions. Thank you.
That's always nice.
Thank you, Berlin.
So basically, if you are, yeah, please.
Yeah, I had a question regarding the runtime context adaptation. Could you please give an example of this? Because that was not totally clear, like the extent of the runtime adaptation.
1 second, I just go back to the slide. So your question, so what exactly is your question? I think I didn't got it right.
Could you give, let's say, a practical example of an adaptation that happened while you were running the experiments?
Right. So a practical example for input signal is essentially the red button on your robot. And that was also what we did in the first case study. So if the robot is like in the environment of a robot, a human, the one that hits a button and the robot stops now. Not when the transition stops firing, but now. That's like the practical example for input signals. And a practical example for output signal or signal clauses is when you want to communicate behavior of the robot to the outside world. For example, if you have a safety automaton, which is the case for our second example. So I'm just sorry for all the slide skipping. Which is the case here. So it's the, I think I can get my cursor here, which is basically here. So you can attach the output signal here and inform, for example, the user about the marking of, within the safety mode, so that he feels safe and knows the robot is aware that he's there. Was that a
Yeah.
good answer?
Yeah, it was indeed. Okay, thank you.
Thank you too.
Roderich?
Yes, can you hear me?
Yes.
Great. Thanks for a fantastic talk. I would like to ask how this relates to controllability, perhaps. So you talked about properties like liveness and reachability, which maybe are related. You may know that there's work by Petri, who looked at whether controllability can be decided for deterministic Petri nets in the context of supervisory control theory, and it depended on the specific formulation of these. And similar to you, is it a decidable problem if it's liveness or not, for example?
So I think we were running basically into similar problems than him, which are, I think, around there. So when we do our model checking and the checking on the properties that we have there, we always go the path of searching for counter examples. So we can't really go generating the full state space and say, okay, everything is controllable, and we know about, for example, the full boundedness of the system. We can't do that. That's really impossible for everything which goes, I think, I don't know, above maybe 5 transitions, whatever. So that's where we have the same boundary in the end, and that's how we also connect with in the end. But compared to the control theory, basically applications that were in his work, we stayed firstly on a much lower level, I would say. So we like aggregate them, and the second thing is how do I describe it? No, that was basically the point. That's the point. Sorry. Yeah.
Thank you.
So,
yeah, maybe I add a little on that, dear Roderich. One issue in this model-driven approach is also that the central specification, where you specify the workflows of the one or many robots, that's actually much smaller than the net that is compiled and refined and is platform specific. So the hope, of course, is that you can at least verify central parts of the abstract net and then leave the other things to the tool set. And the tool set, of course, plays a big role because it refines to the platforms you use. But in the end, verifying a full platform-specific net, of course, is very tedious and almost impossible. But because of the model-drivenness, you can try to at least verify the core of your application.
Thank you, Uwe.